Good morning. I am Dr. Narsinga, Professor of Physics, Dean Research and Development, Marri Reddy Institute of Technology and Management. So today we will study about de Broglie hypothesis, how that hypothesis will be, and how we can experimentally prove that hypothesis. Okay, so that means hypothesis nothing but it will be the particle whenever the particle is moving with some velocity. So it has a particle nature as well as wave nature. So that is de Broglie hypothesis. So he developed after quantum mechanics came into picture. Around 1924, he suggested the Louis de Broglie. He is the PhD student of his father. So he made some suggestion, bold suggestion. What it is means if radiation, which is basically wave, can exhibit a particle nature under certain circumstances, and some other circumstances it behaves like a particle nature. So that means if the electromagnetic radiation or any particle moving with velocity, it has a both particle nature and wave nature. That is his suggestion. But earlier we have different theories. One theory will tell wave nature of the particle, another theory will tell particle nature of the particle. So there are so many discussions going on at that time. So he given the mathematical approach, so where this particle nature and wave nature will exist, this electromagnetic radiation as well as the particle moving with velocity. So that is his suggestion, and that means it will be usually particle as well as wave nature, whatever the material it is exhibit with velocity. Okay, so that means it has he given some mathematical equation, that is lambda is equal to h by p, that is a momentum. Momentum is nothing but h by mv. So that is m is the mass of the particle, v is the velocity, h is the Planck's constant. So lambda is wavelength, that is it is related to wave nature, whereas this mass and velocity is related to particle nature. What we earlier studied, what is meant by wave, what is meant by particle. Okay, so then it will be that equation, how we can derive that equation. So to derivation of that equation, he take the help of Planck's radiation, that is Planck's radiation law. What it means, it is E is equal to h nu, that is a frequency. This is already Planck's theory. It will tells h into nu, that is frequency. Frequency is nothing but c by lambda, that is light velocity divided by wavelength. Then it becomes hc by lambda. Okay, so this equation he derived. So then he made a lambda is equal to how much it will be, lambda is equal to hc by nu, I think. Okay, so then they made some suggestions. So after this, they thought it will be according to Einstein energy mass relation. There is another energy also there. It is related to energy mass relation, that is E is equal to mc square. So if you equalize these two equations, E is equal to mc square and E is equal to hc by lambda, so then the equation becomes hc by lambda is equal to mc square. So C will be cancelled out, then leftover equation will be lambda is equal to h by mc. So this equation what he suggested with this particle is moving with velocity. This is call it as this wavelength is called it as a de Broglie wavelength. So this, if it is a electromagnetic radiation. If it is a particle of mass m and moving with velocity v, then the wavelength of that particle is given by lambda is equal to h by mv. That means it's already c is replaced with velocity of the particle. So that means it is nothing but h by p. Once again, p is the momentum. Momentum is nothing but mass into velocity. So this is de Broglie wavelength. It will be useful for all the applications of this quantum mechanics. Okay, this is the de Broglie equation. This is equation 1 we can say. So then there is another equation you derived. So that is in terms of energy, because the particle is moving with velocity of v. so it has a mass, then it has a kinetic energy also, because particle is moving means it has a kinetic energy. Kinetic energy equation is E is equal to half mv square. So then we can multiply and divide by m, so there will be no harm. That means E is equal to half m square v square by m, because we require the momentum m into v, so that's why we have to multiply m into m multiply divided by m. So okay, so that means E is equal to how much it will be? M square V square is equal to 2m. That means P square, m square V square is nothing but momentum. So momentum is P, that is it will be P square divided by 2m. So whereas that's P, that is once again it becomes if you means cross multiplication, that is 2me is equal to P square. So if P is equal to root of 2me. So this equation coming from kinetic energy relation. Then substitute this p value in de Broglie wavelength. That equation becomes h by root 2me. So this second equation. First equation is lambda is equal to h by p. Second one is h by root 2me. This another representation of de Broglie wavelength. If you know the energy of the particle, then you can directly calculate the wavelength. So if you know the wavelength, how much, if you are required this much wavelength, so then how much energy you want to give, so you know that using this equation, that is lambda is equal to h by root 2me. This is in terms of energy relation. Okay. So another one, this is a particle moving with velocity. Then if it is instead of particle, there is a electron. Electron is moving with velocity, and that it has the mass of the electron. We all know that is 9.1 into 10 to the power of minus 31 kilograms. Whereas the charge, it has a charge also, because it is an electron, it's a negative charge. The charge value is 1.6 into 10 to the power of minus 19. That is the charge value, 1.6 into 10 to the power of minus 19 coulombs. Okay. So this is the charge of the particle, because if the electron is, if you want to move the electron, it requires some potential energy. So you have to apply some potential energy. That is, then only the electron will be accelerate and it will take some velocity. Okay. So then if the electron of mass m, charge e, and if you apply the potential difference, then it will go to velocity of v. Okay. So from these four terms, so we will, how we can derive this de Broglie wavelength, we will see. So because the electron is moving, so then it will be considered as it has some kinetic energy. Okay. So that kinetic energy once again E is equal to half mv square. Whereas electron has energy. So how we can calculate the electron energy? Electron energy is nothing but E is equal to the charge of the electron and potential difference. If the potential difference you applied more, then the kinetic energy will be more. Okay. So that's a relation will be there. E is equal to, that is energy is equal to E into potential difference. This is a capital V we will write. There is a small v and capital V. Please remember those terms, V and small v. Okay. So then we equalize these two equations or two energies, that is half mv square equal to EV. Then the small v, this v square. So then if it is a velocity is equal to how much it will be? Root of 2 EV by m. This is the velocity. Okay, using these two equations, that is kinetic energy as well as energy of electron. So then we know the v value. So we know the de Broglie wavelength also. De Broglie wavelength is lambda is equal to h by mv. Replace v with this equation, root 2 e into capital V by m. So if you replace this v value, so it becomes like this. So if you m enter into inside, so it becomes m square. So that means m square by m, it will be only one m will be there. That m is this one, root of 2m ev, h by root of 2m ev. This is another equation for de Broglie wavelength. It represents electron. Okay. So here the terms h value is equal to 6.62 into 10 to the power of minus 34 joules per kilogram something. Okay. So then there is a mass of the electron, we all know that Mass of the electron is 9.1 into 10 to the power of minus 31 kilograms. So that is the mass of the electron. So then there is a charge of the electron, we know here. Okay. So then substitute all these values in that equation. So then it becomes 12.26. That means lambda is equal to 12.26 divided by wavelength. That is divided by root of capital V. So that is potential difference. So this is in terms of angstroms. Okay. So always the wavelength usually we will keep in terms of angstrom, otherwise we will keep nanometers also. Okay. So if you know the potential difference, then you can calculate the wavelength. Okay. So that way it will be easy to calculate which particle, which potential energy is applied for this particular wavelength. Okay. So that means this is the third equation in terms of electron velocity. So that is 12.26 divided by root V in terms of angstrom, or 1.226 divided by root V in terms of nanometer. So this is the de Broglie hypothesis and their equations. Okay, that's how we can derive the equations, wavelength as well as energy related wavelength and electron wavelength. Okay, these are the de Broglie hypothesis. It will be explained according to this. This mathematically they explained. Okay, so that de Broglie hypothesis, it is around 1924. After 3 years, there is a two scientists, that is Davison as well as Germer. So this they made some experimental. So in that experiment, the de Broglie hypothesis was proved, because due to these two scientists. So in that name of these two scientists, the experiment name itself is Davison and Germer experiment. So they made around 1927. So they want to make some diffraction of the crystal. Okay. So while doing that experiment, so they observed like a wave as well as particle nature, both in that experiment, but in both in not at a time, but in sometimes it will be particle, some other time it will be wave. So that is suggestion by de Broglie. Okay, so that means they demonstrated wave like property of particles. That means particle behave like a waves. That means already particle, it will behaves like a wave. So that means it's a proof of de Broglie hypothesis. How they proved, we will study. Okay, so in that the first time proved the wave nature of the electrons and verified de Broglie equation. So this is a proof of de Broglie equation as well as proof of dual nature of the matter waves. That is also another representation also similar. Okay, so they made 1927, but this de Broglie hypothesis came in 1924. Okay, so this experiment also, it's a proof of quantum mechanics. So in this experiment they have a similar X-ray diffraction type. Okay, so they have this type of experiment. This total will be inside the evacuated things. So if they give some electron beam, then there will be scattered electrons will be there. So they will collect scattered electrons and they will calculate the how it will be behaves like a de Broglie hypothesis. Okay, so in this experiment they have three parts. One is electron gun. So electron gun contains this total part is the electron gun. It contains the filament as well as high potential power supply. Then there is a collimator. So in that collimator there is a small hole will be there. In that hole the electron beam will come out. Okay, so that's electron gun contains. The second one is target. Target is here they used nickel crystal, because nickel has a crystal property. Crystal means it has a arrangement, proper arrangement of atoms. That means if the crystal is like this, okay, so the second layer also similar. So that third one also similar. That means distance between two atoms in every position it will be similar. That is a crystal. If some positions it will be homogeneous, some other place is different, that will be polycrystalline one. Okay, so this one is a crystalline one. So if the one plane to another plane, they call it as a crystalline planes. So this difference between these two planes, the distance is, they call it as a d. So that displacement vector or the displacement between two planes. So this in nickel crystal it will be 0.91 angstroms. This is they calculated already. So this value will be 0.91 angstroms. Okay, that is a crystalline one. That is nickel crystal. So another one is detector. So this detector is a movable detector. So once electron beam is incident on the metal nickel target, then the electrons that beam will be scattered in all directions. But this movable detection, that is only semicircular arc, it will move. Okay, then they will collect the intensity of that electrons. So okay, the how many number of electrons are coming to this area. So then they will collect, then they will, it will give directly intensity of the that experiment. Okay, that is scattered beam. They will be seen from movable detector. It has a sophisticated galvanometer also. So that small points, whatever I told, the electron gun and target, I will explain in another this one also, slide also. So the filament is a tungsten filament. It emits electrons via thermionic emission. Thermionic emission means if you heat up that material, the electrons will be ejected. For that purpose, we have to apply some small voltage. So small voltage, then it will be heated that material and electrons will be ejected. Okay, that ejected electrons will passing through this electrostatic accelerator. This one is a high potential application source. Okay, this is a source for high potential. Okay, so then the electron will be applied this high potential, so that electrons will gain more kinetic energy. Then it will move one place from starting to end point. So at the end point, they will be using collimator. This collimator usage is to reduce the size of the beam, because we have a film means what I am saying is there is a for cameras we have some screens, so or some small holes will be there. So that type of arrangement in collimator it will be there. The number of small cavities will be there. So that will passing through that electron beam, it will cut excess ones. So only small thin layer of the electron beam will be coming from that collimator. Okay, so that is for straight and narrow collimated beam will be accelerated from that collimator, because these all are related to electron gun. It contains the filament, high potential difference application source, then there is a collimator. So these are the related to electron gun. Okay, so that is the one part. Second part is target. The target is only nickel crystal. Okay, pure nickel crystal, that is Ni. The electron beam is fired normally on the nickel crystal. The crystal is placed such that it can be rotated its axis. So there is a crystalline axis of the plane is there, na? That crystalline axis. So it will be rotated. There will be one arrangement. It can rotate in that experiment, because where the maximum intensity will come. So they will arrange this arrangement of crystal rotation. Okay. So that is target one. Next one is a detector. So this detector, it used to capture the scattered electrons. So because it is incident on this, there is a, it's a single crystal, it will be scattered that electrons. So the scattered electrons from the nickel crystal, it will detect. So this detector will be moving in a semicircular arc. It's not a continuous 360 degrees, it will be some angle, it will be okay. So that is shown in a diagram. So that is a detector. These three parts it requires for Davison-Germer experiment. Okay. So then what is the principle behind this? Principle is nothing but it's a wave nature of matter moving with a moving electrons. That means electrons moving with velocity, it has a wave nature. That's a basic principle of this experiment. So that electron gun, which consists of filament heated by low battery, not I told, the B1 produces electron. These electrons are accelerated to desired velocity by applying suitable potential from high tension source, that is the B2. So then the accelerated electrons are collimated into fine beam by allowing them to pass through a system of pinhole provided in the cylinder C. That is a electron gun, target and cylinder. So these fast moving electrons is made to strike the target, that is a nickel crystal. So then the electrons now scattered in all directions. Once it will be incident on that nickel crystal, it looks like a glass plate. So then it's every corner, the scattered light will be going out. That is, electrons will be going out. These scattered light, it will be collected through sensitive galvanometer, whose deflection is proportional to the intensity of the electron beam entering the collector. So in the collector, we have a sensitive galvanometer. So this work of this galvanometer is, whenever the deflection is there, it will convert into intensity. Okay, so that is the collector job, to make a sensitive galvanometer to give the intensity of the beam. Okay, so the intensity of the scattered electron is not continuous. That means the intensity of the scattered electron, it is not continuous. That means it may not be constant throughout the angles. Okay, so sometimes it will be show maximum, sometimes it will be minimum. So it shows the maximum and minimum values. So you can see here there is a two observations. While doing this experiment, they got two observations. One observation is around 54 volts. Around 54 volts, they got maximum intensity of the beam. So that means around 54 volts here, the kinetic energy, that means is applied voltage from high voltage power supply. They applied 54 volts, then you will get the maximum intensity of the scattered electrons. That means number of scattered electrons at this angle more. Okay, so that means at this angle it will be maximum intensity. If you go beyond, that means less than this voltage or more than this voltage, the number of electrons ejecting is less, depends on the angle. Okay, so that means this angle is also important, as well as the voltage also important. But this when it will be maximum, it maximum at theta is equal to 50 degrees. Once the scattered angle, that means scattered angle is nothing but the incident ray and scattered ray. So the angle between these two is a 50 degrees, then only you will get the maximum intensity. That is the second observation. First observation is this angle and 54 volts. This is the first observation. When 54 volts, they got maximum intensity. And that maximum intensity also comes from this incident and scattered one is 50, when 50 degrees. That is also another observation. When theta is 50 degrees, this 54 volts electron beam is incident maximum. Similarly, if the theta also, if the theta value is less, then you will get the less intensity. More also, more than that 50 also, it will be less. So at particular value, it will be maximum. The 50 degrees, it will be maximum intensity will come out. Okay, so that also depends on the 54 volts. These two are interrelated. If there is using 50 volts, so you are 50 degrees, you won't get the maximum. Okay, so you are using 54 volts, you want to 40 degrees, then only it is also not coming. So there is a two interrelated observations. One is 50 degrees and 54 volts. These two are observations of Davison-Germer experiment. From these two observations, how they will make de Broglie hypothesis correct. Okay, that we will see that. Okay, so the observed values of scattering angle is 50. So that means the incident to incident ray and scattered ray. So the angle is 50 degrees. This 50 degrees is surface of the crystal. But crystalline plane, it may not be same. Crystalline plane may be different. That means the crystalline plane angle and this angle, it will be different. The incident and crystalline planes will be like this. Okay, so then angle of this incident and scattered from Bragg planes are crystal planes antam. So we will say crystalline planes are Bragg planes. So this angle is around 65 degrees, not 50 degrees. So that means crystalline plane to incident to crystalline, then it will go to scattered. So this angle, it becomes 65 degrees. Whereas incident, this one in surface, it will be 50 degrees, but crystalline planes, it will be 65 degrees. Okay, so that will be 65 degrees we use in our calculations. Okay, so that means at scattering angle of 50 degrees, the d value from X-ray scattering is 0.92 angstroms, that is from nickel crystal. Okay, So using Bragg equation, what is mean by Bragg equation? Whenever the Bragg equation follows or it will reach, then only you will get the intensity. That equation is 2d sin theta is equal to n lambda. So in this one, n is the first order diffraction, that is the 1. Lambda value we have to calculate. 2 is the number. D is the displacement vector or the interplane distance, that is 0.92 angstroms. Okay. Then sin theta. Theta is, instead of 50, we have to use 65 degrees. Then the n is equal to 1. Using all these parameters, you will get the lambda is 1.67 angstroms. This is the diffraction side. That means its angle means it will be diffracted ray. Okay. So then what about particle nature? Then this first observation, another observation is potential difference, that is 54 volts. So potential difference means the electron will be ejected. So that means electron means once again it will be particle. But that particle is same velocity, same wavelength or not, we will check. Okay. So using the potential difference, the de Broglie wavelength we have equation, that is 12.26 divided by root capital V, that is potential difference. So that value, this root of 54, that means it will be around 7.8. So 12.26 by 7.8. So it becomes 1.66 angstroms. So you can see with these two observations, one is 1.66 angstroms, another one is 1.67 angstroms. So these two are close together. So that's why they will say it will be de Broglie hypothesis proved experiment is Davison and Germer experiment. This is the first proof of experimental proof of de Broglie hypothesis, Davison Germer experiment. So that is a Davison Germer experiment is proof of de Broglie hypothesis or proof of dual nature of the particle. This whatever we said, it will be same. That is dual nature as well as de Broglie hypothesis. These two are same meaning. Okay. So this is Davison Germer experiment. Then we will go for another. There is in according to quantum mechanics. So there's all this particle is moving like a wave. So the wave means we cannot identify exactly where it will be. Okay. So the wave nature, for that purpose, there is a Schrödinger, a scientist from German. So in 1926, he made some mathematical equation. So it will tells that the wave is moving with velocity v and mass is m. So then it will be group of waves. If you just drop one means sand in water, so there is a number of waves will come. So that's a group of waves. They written one mathematical equation for general mathematical equation for wave function. So that is nothing but psi is equal to psi naught sin omega t minus kx. In some books, they will write psi is equal to psi naught exponential also minus omega t by kx something. Okay. So this way also they will write, but I will write this way, it will be easy. So psi is equal to psi naught sin omega t minus kx. So how it will be represented? Psi means it's only mathematical representation. So what it will tell? That wave function. Okay. So psi naught is nothing but the amplitude of the psi wave. So amplitude means one crest, one this one. This distance we call it as a amplitude. Okay. So that amplitude tells the psi naught, and wave will be along. It looks to be sine wave, and omega is the angular velocity. Okay, angular velocity. Then t is the time, and k, it will be wave vector. K is equal to 2 pi by lambda. That is a wave vector. Then x is the position. Which position it will be, like these positions in that wave. Okay. So that is a general wave equation. It represents position as well as time. Okay. So then if you want, this equation is nothing but it's a time independent wave equation. So in the time independent wave equation, we have to eliminate the time term. For that purpose, what they did, they differentiate this wave equation with respect to x. That is partial differentiation. Okay. partial differentiating with respect to x. So what will happen? The equation becomes dou psi by dou x is equal to psi naught cos omega t. Sin is the cos omega t minus kx. The parameter is a constant of k, that k will be coming outside, minus k. So this equation minus k psi naught cos omega t minus kx. But still the t term will be there. So once again, with respect to t, x, we have to differentiate this equation one more time. So that means dou square psi by dou x square is equal to minus k psi naught, that is cos will be minus sin, that is minus sign will be there, minus sin omega t minus kx into once again minus k. So this minus k it will be k square, then minus sign is 1 minus will be coming out because of the 3 sign minus. So k square psi naught sin omega t minus kx. So this double differentiate equation. So where we know that this psi square psi 0 sin omega t minus kx is nothing but psi in that wave equation. Wave equation is psi is equal to psi naught sin omega t minus kx. Substitute this psi, so it becomes dou square psi by dou x square is equal to minus k square psi is the equation. So minus k square go to other side, it becomes dou square psi by dou x square plus k square psi is equal to 0. So this equation, so where we have to remove this k value. The k value is nothing but wave vector is 2 pi by lambda. So if it is a k square, it will be 4 pi square by lambda square. So you substitute this value in the k place, that becomes dou square psi by dou x square plus 4 pi square by lambda square psi is equal to 0. This is one equation. Okay. So then we have this is actually classical wave equation. So here the term lambda, that is if you take the de Broglie wavelength, then it becomes quantum mechanics term. Okay. So the lambda we can say any different types, like our red light also one lambda value is there 7000, but usually this particle electron, it will be 1.66 angstroms. So that's a lower particle side, we will use the quantum mechanics. At higher particles they use classical wave. Okay. So it will be classical differential equation. Okay. But if you substitute the lambda value, we know that de Broglie wavelength, that is lambda is equal to h by mv, we have to substitute here, that h by mv is substituting here, that means dou square psi by dou x square plus 4 pi square into h by mv square, that is m square and v square it will come, because it's a lambda square value. So the lambda square is equal to h square by mv. Here they just h by mv whole square they written. Okay, m square v square. Substitute that value, that equation becomes dou square psi by dou x square plus 4 pi square m square v square psi divided by h square is equal to 0. Okay. So then it's once again the velocity term came into picture. The velocity is nothing but the displacement, that is displacement by time, rate of displacement, that is nothing but velocity. So once again there is a time term is coming, so we have to eliminate that time term. For that purpose, because the particle is moving with velocity, so then we will take the help of energy of the particle. So the total energy is in terms of kinetic energy plus potential energy. Okay. So the total energy, kinetic and potential energy. So kinetic energy we know that half mv square. So substitute these values, then total energy is equal to half mv square plus v. So then mv square is equal to, so this 2 will go other side, v will be another side, then 2 into e minus v. So then we multiplied m divided by m, there will be no harm, then m square v square becomes 2m into e minus v, or both sides we will multiply the m. So 2m into total energy minus potential energy. This is not a potential difference, this is a potential energy once again, that is another term. Okay, 2m into e minus v. Then this m square v square, replace m square v square by 2m into e minus v. So that becomes dou square psi by dou x square plus 8 pi square m into e minus v divided by h square into psi is equal to 0. So this is the time independent wave equation for Schrodinger in a one dimensional, only along x axis. So if you want to write 3D, that is 3-dimensional, then you have to replace this dou square psi by dou x square, that is in replaced with del square, that is dou square psi by dou square by dou x square plus dou square by dou y square, like that. Del square means, so in 3-dimensional, what I mean is dou square psi by dou x square plus dou square by dou y square plus dou square by dou z square. Here ij case will be there. Okay. So that's a 3-dimensional equation. So instead of this, they will write del square psi is equal plus 8 pi square m into e minus v by h bar square into psi is equal to 0. So this they also write, instead of this, they just write del square psi. Okay. So this 3-dimensional equation, if you write a del square psi. Okay. So that is also time independent Schrodinger wave equation for 3D. So today we studied about de Broglie hypothesis and derivation. Then we have Davison-Germer experiment. Then there is a Schrodinger time independent wave equation. Okay. Thank you.